In the year 2026, we find ourselves at a crossroads of efficiency and raw power. Every square micrometer of a chip is a precious piece of real estate, more valuable than the finest land in any metropolis. This journey is not merely about understanding a circuit, but about mastering the art of the controlled switch. We will explore how transistors act as gatekeepers, the inherent flaws they carry, and the clever ways engineers fix those flaws. By the end of this exploration, you will see the world of electronics not as a collection of parts, but as a delicate balance of logic and electricity. At its core, past transistor logic is a departure from the traditional way we think about CMOS circuits. In a standard setup, we have two teams working against each other, the pull-up network and the pull-down network. One side pushes the signal to the sky, while the other pulls it to the earth. Past transistor logic changes the game by treating the MOSFET as a simple, elegant switch. It does not actively drive the output to a voltage rail in the same way, but rather opens a path for the input to become the output. This is a subtle shift, but it changes everything about how we calculate speed and space. Imagine a hallway with a series of doors, where each door represents a transistor controlled by a specific key. When the key is turned, the door opens and the person walking through carries the information to the next room. In this analogy, the person is the logic level, and the door is the past transistor. If the door is closed, the information is isolated, held back by the high resistance of an empty space. This concept of propagation, rather than constant regeneration, is what makes past transistor logic so fascinating and yet so dangerous. To understand the present, we must look at the fundamental nature of the tools we use, specifically the NMOS and PMOS devices. An NMOS transistor is like a bridge that lowers when it receives a positive signal at its gate. It is exceptionally good at carrying a zero, a strong connection to the ground that leaves no room for doubt. However, when it tries to carry a 1, it falters, losing a bit of its strength due to the threshold voltage. It is a creature of the earth, strong in the depths but weakening as it reaches for the heights. The PMOS transistor is the inverse, a mirror image that functions best when the world around it is quiet. It excels at passing a strong one, a pure signal from the power source that remains untainted by the passage. Yet, when asked to pass a 0, it struggles, leaving a small residue of voltage behind. This fundamental asymmetry is the original sign of past transistor logic. It means that no single transistor is perfect, and every choice we make in design involves a trade-off between purity and simplicity. Why would we accept these imperfections when standard CMOS is so reliable? The answer lies in the ruthless pursuit of efficiency and the reduction of transistor counts. In the world of VLSI design, fewer transistors mean less area, less weight, and often, less power. Past transistor logic can implement complex functions, like an XOR gate, using a fraction of the components required by traditional methods. This reduction in the physical footprint allows for denser chips, packing more intelligence into the same grain of sand. This efficiency goes beyond just the number of parts. It extends into the very way we size those parts. In standard CMOS, we must carefully balance the size of PMOS and NMOS transistors to account for their different speeds. Because holes move slower than electrons, the PMOS must often be 2 or 3 times larger than its NMOS counterpart. Past transistor logic often bypasses this ratioed headache entirely. By using a single type of transistor for many operations, we create a ratio-less design that is easier to lay out and more predictable in its geometry. However, the path of efficiency is rarely a smooth one, and the threshold voltage problem is our first major obstacle. When an NMOS transistor passes a high signal, the output never quite reaches the full potential of the power supply. It stops short, reduced by a value known as the threshold voltage, which acts as a tax on the moving signal. If the supply is 1.8 volts, the output might only reach 1.3 volts. This loss creates an ambiguity, a gray zone where the next gate in the chain might not be sure if it is seeing a high or a low. This problem becomes a nightmare when we begin to cascade these gates in a series. Imagine a message being whispered from one person to another, but each person loses a few words of the sentence. By the time the message reaches the 5th or 6th person, it has become unintelligible noise. In a circuit, if we use the output of one past transistor to drive the gate of another, the threshold losses add up. Eventually, the signal becomes so weak that it can no longer trigger a response. and the logic of the machine collapses into silence. There is a vital distinction we must make here, one that separates a master designer from an amateur. There is a difference between cascading gates and simply connecting transistors in series. If we have a long chain of transistors all controlled by full-strength gate voltages, we only lose the threshold voltage once. The first transistor takes its tax, but the subsequent ones find the signal already reduced and let it pass without further penalty. It is only when the weak signal is used to control the next gate that the degradation becomes cumulative and terminal. We must also consider the hidden enemy of every high-speed circuit, the RC delay. Every transistor has an internal resistance when it is turned on, and every connection has a parasitic capacitance. When we chain these together, we create a distributed network that acts like a sponge, soaking up the speed of the signal. The time it takes for a voltage to rise or fall increases quadratically with the number of stages. A chain that is twice as long does not take twice as long to respond. It takes 4 times as long, making long series connections a dangerous gamble. In the pursuit of speed, we must also be wary of the sneak path, a silent killer of battery life. A sneak path occurs when the logic is designed in such a way that a direct connection is accidentally made between the power supply and the ground. This creates a short circuit that doesn't necessarily break the chip, but it causes a constant leak of energy. This static power dissipation ruins the primary advantage of CMOS technology, which is its ability to stay cool and efficient when it is not actively switching. Then there is the haunting problem of the floating node, a point in the circuit that is connected to nothing. When all the transistors connected to an output turn off, that output becomes a stray island in a sea of silicon. It holds onto whatever charge it had last, but that charge can slowly leak away due to noise or temperature. A floating node is unpredictable. It can be read as a 1 or a 0 depending on the time of day. In a world of absolute logic, unpredictability is the ultimate failure, leading to errors that are nearly impossible to debug. To solve these problems, we turn to the structure of the multiplexer, which serves as a blueprint for safe-pass transistor design. A multiplexer is a selector, a device that ensures only one path is active at any given time. By using complementary control signals, we can guarantee that the output is always connected to a valid input. This eliminates the possibility of a floating node and prevents sneak paths from ever forming. It is the transition from a chaotic collection of switches to a disciplined, structured flow of data. Building a 2-to-1 multiplexer is the first step in this disciplined approach. We use 2 pass transistors, one for each input, and control them with a signal and its inverse. When the selection signal is high, one path opens. When it is low, the other path takes over. This simple arrangement allows us to route information with surgical precision. We can even scale this up to a 4-to-1 multiplexer, using a tree-like structure to navigate through more complex decisions without adding unnecessary bulk to the design. The true beauty of this approach is revealed when we realize that every standard logic gate can be derived from a multiplexer. An AND gate, an OR gate, even the complex XOR gate can all be seen as specific configurations of a multiplexer's inputs. We no longer need to memorize truth tables as if they were static laws. Instead, we use Boolean expressions to guide which signals should be passed to the output. This intuition allows a designer to see the logic in the movement of the electrons, rather than just in the symbols on a page. But we must return to our original sign, the degraded signal that haunts the NMOS switch. Even with a perfect multiplexer, the output of an NMOS network will still suffer from that threshold voltage drop. To fix this, we introduce the level restorer, a small but powerful circuit that acts as a guardian of the truth. It consists of an inverter and a tiny PMOS transistor. When the output starts to rise toward a weak one, the inverter detects the change and turns on the PMOS, which pulls the output the rest of the way to the power rail. This level restoration is like a refresh button for our logic. It takes a signal that is tired and sagging and breathes new life into it, ensuring it is a crisp, clean one. However, this fix comes with its own price. The restorer must be weak, enough so that the main pass transistors can overpower it when they need to pull the signal back down to 0. It is a delicate tug of war, a balance of strengths that must be carefully simulated and tested to ensure the circuit doesn't get stuck in a permanent state of indecision. As we look back at the landscape of pass transistor logic, we see a methodology defined by its contradictions. It is smaller, yet more fragile. It is faster in some ways, yet slower in others. It is not a universal replacement for standard CMOS, but rather a specialized tool for the expert craftsman. It is used in the heart of microprocessors, in the arithmetic logic units where every bit of saved space allows for more computational power. It is the secret sauce that allows our smartphones to be thin while remaining incredibly smart. The lesson we can draw from this is that in engineering, as in life, there is no such thing as a free lunch. Every gain in efficiency requires a corresponding increase in our awareness of the underlying physics. If we want to build things that are smaller and faster, we must be prepared to handle the complexity that comes with those reductions. We cannot ignore the threshold losses of our own choices. We must build restorers into our systems, whether they are technical systems or the habits we use to manage our daily lives. In our own existence, we often try to take shortcuts, seeking the past transistor route to success by doing more with less. But we must ask ourselves, are we losing the voltage of our purpose along the way? Are we cascading our efforts so thin that the final result is unrecognizable noise? True mastery is knowing when to use the shortcut and when to invest in the full, robust CMOS approach of hard work and redundancy. It is about the balance between the switch that lets things pass and the driver that pushes things forward. As you go about your day, think about the invisible logic gates that surround you. Think about the billions of switches firing every second to bring you information, entertainment, and connection. Each one of those switches is a testament to the human ability to negotiate with the laws of physics. We have learned to turn the flaws of silicon into the virtues of computation. We have learned that even a weak signal can be restored if we have the right structure in place to support it. I hope this deep dive into the philosophy and physics of past transistor logic has given you a new perspective on the world of silicon. Engineering is more than just math and circuits. It is a way of thinking about the limitations of reality. I wish you all great health, clarity of mind, and the strength to restore your own signals whenever they grow weak. Please don't forget to subscribe to the channel so we can continue this journey together through the wonders of the digital age. Until next time, keep your logic sharp and your connections strong.